Dear students, today I am going to discuss about combination of cells. Like combination of resistors, we can join the cells in series or in parallel, or the mixed combination of series and parallel. So the purpose of joining the cells in series or in parallel or mixed combination is to get more potential difference or more current in the circuit. For example, when we use a cell in the torch, we are not using just a single cell. There we use 2 or 3 cells connected in series. The reason is, if you take only one cell, it just provides an EMF of 1.5 volt. The bulb is designed to operate at 3 volt. So then we have to connect 2 cells in series so that the EMF, total EMF or equivalent EMF, I can say 3 volt. So the same process or same steps involved in any working of any devices where we need to join 2, 3, 4, 5 cells in series or in parallel. We have both the type of combinations, series combination also, parallel combination also in daily life use. So firstly, let me explain 2 terms related to combination of cells. First one, equivalent EMF. In resistors I have discussed about equivalent resistance. In resistors, equivalent resistance means it is the resistance of a single resistor which produces the same effect as that of the combination produces. For example, 2 ohm, 3 ohm, 4 ohm, 3 resistors joined in series. Effective resistance, instead of the 2 ohm, 3 ohm and 4 ohm, we can use a single resistor of resistance 2 plus 3 plus 4, 5 plus 4, 9 ohm resistor as a single, so that it will produce the same effect as the combination of 3 resistors 2 ohm, 3 ohm and 4 ohm produces. So likewise here also we have equivalent EMF. Equivalent EMF. So the name says it is something equivalent to combination of EMFs. So I discussed in the previous class, that EMF is electromotive force. It is the potential difference across the terminals of a cell when no current is drawn from the cell. Potential difference across the terminals of the cell means ends of the cells when no current is drawn from the cell. That is, it is in open circuit. Just measure the PD, potential difference, across the ends of the cell, that is positive and negative terminals. It will show certain voltage or potential difference. With the help of a voltmeter you can measure, but we have to use ideal voltmeter, so that what reading it shows, ideal voltmeter, say 1.5, then EMF we can take it as 1.5 volt. So equivalent EMF means it is the EMF of, it is that EMF of the combination which produces the same effect as that of the combination. When a number of cells are connected in series or parallel, certain EMF, if you find, that value of EMF is the effective of or equivalent to all the values of EMFs in the circuit of cells. Okay, then equivalent internal resistance. If you replace the particular value of internal resistance from a number of cells, so which will provide the same effect as that of the combination of cells. Okay, so those two are the 2 terms which we are going to derive in series and parallel combination. That is, firstly we derive for equivalent EMF, then equivalent internal resistance. Firstly, I am going to derive the expression for equivalent EMF and equivalent internal resistance when cells are joined in series, then we extend the rule to the 3 and more number of cells in series. Firstly, we have to show one diagram how we can join the cells in series. So series combination means it is end-to-end connection. Means after one cell there will be another cell. After that another cell. After that another cell. Means they are not connected between 2 points. They are connected one after another. One after another. One cell, another. Means positive terminal of second cell connected to negative terminal of the first cell. This is the combination used in the torch normally when 2 or 3 cells are joined. Okay, in a torch. Battery cells we use. There we use 2 cells normally or sometimes 3 cells. Okay, so then 2 cells joined in series here. Current drawn from both the cells should be same in series combination, like in resistors in series. So current leaving is I from the first cell, positive electrode, whereas current entering the negative electrode is also I. Okay, here also the current is I, and the current entering the negative electrode of the second cell is also I. That means the same current is passed through the 2 cells. Here the derivation is about 2 cells, equivalent EMF and equivalent internal resistance of 2 cells in series. So the same current flows through both the cells. And let the EMFs be epsilon 1 and epsilon 2 and internal resistance be R1 and R2 respectively for the 2 cells. And terminal PD. Now actually this is an incomplete diagram. We can put one external resistance for this, but not necessary for the derivation's sake. That's why I didn't show it. Okay, we can complete the circuit. We can make it a closed loop so that there is a external resistance, say capital R, connected to the circuit, but not necessary for the derivation part. Okay, so now the same current flows through both the cells. That's one thing. EMFs epsilon 1 and epsilon 2, internal resistance R1 and R2 for the 2 cells respectively. Terminal PD or potential difference across first cell is VAB between the terminals V and B. Means the cell 1 is connected between the points A and B. Hence its potential difference or terminal PD is VAB. And cell 2 with EMF epsilon 2 connected between the points B and C. Terminal PD or potential difference across the cell 2 is VBC. And then total PD across the combination of 2 cells between points A and C, that is noted as VAC. So just there is no connection, just I said it is the potential difference between this point and this point is VAB. Potential difference between B and C is VBC. Potential difference between A and C is VAC. Now I said equivalent EMF and equivalent interactions. Now, okay, what I do? I replace these 2 cells with a single cell which produces the same EMF as that of the combination, that is equivalent EMF, and which produces the same opposition, that is equivalent internal resistance REQ. So instead of 2 cells with EMF epsilon and epsilon 2, a single cell of EMF epsilon EQ and internal resistance REQ connected between the points A and C. Okay, between the points A and C. So instead of a combination of 2 cells in series, I take one cell with the EMF called as equivalent EMF epsilon EQ and internal resistance, that is equivalent internal resistance REQ. Terminal PD of this equivalent cell is VAC between the points A and C. That is, this single cell is connected between points A and C instead of these 2 cells. So that is called as equivalent cell. Now the derivation part. So in the previous class we have discussed the relationship between terminal PD, EMF and internal resistance in terms of current. Okay. So the terminal PD across the cell or EMF across the cell, we can directly write here. So firstly I write terminal PD across the first cell. Okay, the cell 1 is this and this is the cell 2. Okay, terminal PD, I shortly write potential difference or potential drop, you can say, across first cell, okay, is VAB equal to EMF epsilon 1 minus current I through the cell and internal resistance R1. This is the terminal PD across the first cell, VAB. Similarly, terminal PD across the second cell, PD across the second cell, is VBC equal to, between points B and C, what is the potential difference or terminal PD? Because there is a current flow which is equal to I. So terminal PD across the second cell is epsilon 2 minus IR2. So this is the relation which connects the potential difference across the cell or terminal PD, EMF, current and internal resistance of the cell. So now total terminal PD, VAB is this much, VBC is this much, total terminal PD across the combination of two cells. Okay, so total PD across the combination, PD across combination of cells is VAC. VAC is the total PD from point A to from C. Between points A and C, we want to write terminal PD. So observe carefully, VAC is VAB plus VBC. So VAB plus VBC. Okay. So this can be written as, okay, substituting VAB is EMF epsilon 1 minus I into R1 plus VBC is epsilon 2 minus IR2, I into R2, internal resistance. Now we can write here that is equal to epsilon 1, epsilon 2, I group together. Okay, so VAC equal to epsilon 1 plus epsilon 2. Okay, then I is common in both the terms, IR1 and IR2. So minus I times R1 plus R2 minus I into R1 plus R2, because minus I is common for both the terms IR1 and IR2. So this is equation number 1 I will take. Okay. So now I can apply the same rules for the equivalent cell, that this particular circuit. Okay. So for the equivalent cell, terminal PD is how much? Terminal PD across equivalent cell is, terminal PD across equivalent cell is VAC, I can write. So VAC equal to equivalent EMF epsilon EQ minus current I in the circuit, into REQ, equivalent internal resistance. So this I will take as equation number 2. This is equation number 2. Then comparing equation 1 and equation 2, what I get? So here VAC and VAC same in LHS. So RHS we have to compare. So I write epsilon EQ minus I into REQ equal to, here what is there in RHS? Epsilon 1 plus epsilon 2, EMF of first cell plus EMF of second cell. So that is epsilon 1 plus epsilon 2 minus current I into R1 plus R2. Okay, now I think you can easily guess epsilon EQ is equal to epsilon 1 plus epsilon 2. Okay, and Req. You see, here I is there, here I is there. Req is in place of R1 plus R2. Okay, so R1 plus R2. So this is the expression for the equivalent EMF, and this is the expression for equivalent internal resistance when we join two cells in series. And you can extend this rule to 3 or 4, 5, etc. cells. In general, epsilon EQ, if n cells with EMFs epsilon 1, epsilon 2, epsilon 3, epsilon 4, etc., epsilon n joined in series, then equivalent EMF can be written as epsilon 1, epsilon 2, epsilon 3, etc., etc. You have to add as many terms as the number of cells are present. Okay, so last is nth cell, EMF of nth cell. And similarly, equivalent internal resistance Req equal to R1 plus R2 plus R3 dash 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 Rn. Okay, so this is the equivalent internal resistance. So we can write the conclusion here. When a number of cells are joined in series such that negative terminal of one cell connected to positive terminal of the second cell, then the equivalent EMF is equal to sum of the individual EMFs of the each cell. Sum of the individual EMFs. Sum, adding all the EMFs. Similarly, equivalent internal resistance is equal to sum of the individual internal resistances. So this is the rule for series combination of cells. Now one special case comes. Suppose the two cells are joined like this. Positive terminal like this and negative terminals joined together such that current comes out of first cell, positive terminal of first cell, positive electrode of first cell. Okay, current entering the positive electrode of second cell with EMF epsilon 2. Okay, internal resistance R1 and R2. Then in this case, equivalent EMF epsilon EQ can be written as epsilon 1 minus epsilon 2. This is the equivalent EMF. Suppose the two cells are joined, it is quite opposite. Second cell is connected reverse here. Normally, positive electrode of second cell connected to negative electrode of first cell, and positive electrode of third cell connected to negative electrode of second cell. That will be the series combination. But if or by chance, if the negative electrode of second cell connected with the negative electrode of first cell, then current enters the positive electrode of the second cell and current leaves the positive electrode of the first cell. Assuming that EMF of first cell is more than EMF of second cell, then we can write equivalent EMF of this combination is epsilon EQ equal to epsilon 1 minus epsilon 2. Whereas the equivalent internal resistance is R1 plus R2 only, same, no change, no minus. Not R1 minus R2, wrong it is. It is adding only. The reason is the resistance has no polarity, plus and minus. Only potential difference we take strictly the sign plus and minus. Okay, so here minus are joined together. Okay, so that's why the equivalent EMF should be taken like this. Now this is about a series combination of two cells. I have here first cell with EMF epsilon 1, second cell with EMF epsilon 2. Equivalent EMF I get epsilon 1 plus epsilon 2, and we can extend the rule to n cells like this. Okay, so next we have parallel combination of cells. The same derivation, that is when a number of cells joined in parallel, expression for equivalent EMF and equivalent internal resistance. Basically we take two cells connected in parallel. Okay, so derivation of the expression for equivalent EMF, expression for equivalent EMF and equivalent internal resistance when two cells connected in parallel. When two cells connected in parallel. Okay, so now I have to join two cells in parallel. Okay, so the connection for the circuit diagram can be. Okay, so the circuit diagram is like this. So we have studied in resistors. Whenever we want to connect in parallel, we have to connect between two fixed points. Okay, so I have one cell here with EMF epsilon 1 and internal resistance R1. I have another cell whose EMF epsilon 2 and internal resistance R2. Sometimes in the question they may give E1 and E2. Okay, E1 and E2 also they can give the EMF. No problem. If the question gives the symbols E1 and E2, you would have to take E1 and E2 for the derivation part. Okay. Internal resistance denoted by small r1 and small r2. Now parallel combination means the two cells are connected between so the points, 2 points A and B like this. Okay, so this is the parallel combination. Okay, so the current leaves the first cell from positive electrode like this, current I1. Current leaves from second electrode, say the second cell positive electrode, it is I2, and total current flowing out of the combination is I, and here also current entering the junction. Okay, so here first cell gives current I1, second cell gives current I2, and now we have to get the potential difference or terminal PD across the combination that is same for both the cells. So between the points A and B, so between the points A and B, two cells are connected parallelly. So the potential difference for the first cell, potential difference for the second cell is the same between the points A and B. Let V be the terminal PD for the two cells. It is parallel combination, so terminal PD will be same for both the cells. In series combination, current will be same for both the cells. Here currents are different, EMFs are different, internal resistance are different. Okay, they may be same also sometimes. The EMF and internal resistance can be same if you take identical cells. Okay, like torch, normally the cells are identical. When you take purchase a cell freshly, normally they have equal value of EMF and equal value of internal resistance. Now this is equivalent to a single cell of EMF epsilon EQ and internal resistance REQ. The potential difference or terminal PD of the equivalent cell is V between the points A and B. Between the points A and B, equivalent EMF is epsilon EQ and the terminal PD of the equivalent cell. Terminal PD of the equivalent cell is V. Equivalent internal resistance REQ, equivalent EMF is epsilon EQ. Then now I have to join the now I have to explain how the currents you have to take in combination of resistors. Parallel combination of resistors, we have seen the currents are added up. So the same here, that is current I coming out of the point A or leaving the point A is I, and current entering the point A or junction or node is I1 and I2. So it is I1 plus I2. Okay, so I equal to I1 plus I2. Now what you have to do? We have to write the expressions for I1 and I2. Okay, let me take it as equation 1. Now the relation between EMF, terminal PD, current and internal resistance we have to write. So the terminal PD again I can write terminal PD for first cell. Terminal PD for first cell or across first cell I can say. Across first cell. First cell is the EMF epsilon 1, internal resistance R1. Okay, first cell is V equal to EMF epsilon 1 minus I1 R1. Okay. Now I want to substitute I1 here in this above expression. So I have to rewrite this expression to get I1. I bring minus I1 R1 to the LHS equal to epsilon 1 minus V. I don't want R1 here, take into RHS, so I1 equal to epsilon 1 minus V divided by R1. So this I will take as equation 2. Similarly, terminal PD across the second cell. Okay, terminal PD or potential difference across the second cell. PD across second cell is V equal to epsilon 2 minus I2 R2. Okay, because the cell has EMF epsilon 2, current drawn from the second cell is I2, resistance, internal resistance is R2. V is same. Why? Terminal PD should be safe when two cells or three cells joined in parallel. Potential difference between the points E and P will be the same. So this implies directly right. Okay, so V equal to epsilon 2 minus I2 R2 becomes I2 equal to current I2 drawn from the second cell equal to, it's very similar expression to the previous as first cell, that is epsilon 2 minus V divided by R2. So this I will assign equation 3. Okay. Now what I do, I have equation 1 where the total current drawn from the two cells is sum of the currents. Thus total current I becomes I1 plus I2 I have to get. Substituting for I1, epsilon 1 minus V divided by R1 plus second cell, current drawn from second cell is epsilon 2 minus V by R2. Okay, so this is the current separately. Now we can write epsilon 1 by R1 plus epsilon 2 by R2. What I do, first epsilon 1 by R1, epsilon 2 by R2 I write together. Okay, this side together. Or take together, okay, minus V common here, V by R1 minus V by R2, so I will take V outside. So that is 1 by R1 plus 1 by R2. Okay, so this is the total current I. So then next, this equation I will take it as equation number 4. Okay, equation number 4. Now what I do, I have to apply the same rule to the cell which is equivalent cell. Okay, what happens to the equivalent cell? The relation between terminal PD, EMF, current and internal resistance for the equivalent cell is, for the equivalent cell or terminal PD only I write terminal PD across equivalent cell. Okay, so that is V equal to EMF is epsilon EQ, terminal PDV, same as a combination of these two cells in parallel, same terminal PD, minus equivalent EMF epsilon EQ I will take, then I will take current I into REQ. Okay, current I into REQ. Then next we can rewrite this as I equal to, okay, so if you bring I into REQ LHS, minus becomes plus. The next epsilon EQ minus V in the RHS. I into REQ equal to epsilon EQ minus V. So hence I equal to epsilon EQ minus V divided by REQ. So this is the expression we get, epsilon EQ minus V by REQ. Equation number 5. Okay, equation number 5. Okay, one more step I can continue here. Okay, so now what happens, you see this expression I equal to last part. Okay, this I can write here only. This implies I equal to epsilon EQ divided by REQ minus V divided by REQ. Okay, so this is the expression I write as number 5. Comparing 4 and 5, you can write. Okay, so comparing 4 and 5, I can continue this. Okay, epsilon EQ, okay, divided by REQ which is there in the RHS of equation 5. Here I have comparing equations 4 and 5. Observe carefully. Epsilon 1 by R1 plus epsilon 2 by R2. Here epsilon EQ by REQ is there. So epsilon EQ by REQ equal to epsilon 1 by R1 plus epsilon 2 by R2. We can write. Okay, so this is the first part. Then second part, see, compare I and I, LHS, RHS V and V is compared. So here this bracket 1 by R1 plus 1 by R2. In this equation of 5, 1 by REQ. So thus I can write 1 by REQ equal to 1 by R1 plus 1 by R2. Okay, this is the expression for equivalent internal resistance. We can simplify this. Okay, taking LCM both the RHS, that is R1 R2 equal to, okay, so 1 by REQ, let it be same in the LHS. RHS R1 into R2 is a common denominator. Numerator will be R2 plus R1. Thus equivalent internal resistance, firstly equivalent internal resistance for two cells in parallel can be written as REQ. So here I have 1 by REQ equal to R2 plus R1 by R1 R2. When I take REQ, I have to take reciprocal. Reciprocal means the numerator denominator gets interchanged. So 1 by REQ is there, I write REQ. So R1 R2 goes to numerator in the RHS. Denominator I can write R1 plus R2. So this is the equivalent internal resistance of the combination of two cells in parallel. Okay, this is very similar to the resistors in parallel. In resistors in parallel, RP expression I gave R1 R2 by R1 plus R2 for two resistors. Here also same, R1 into R2 by R1 plus R2 is the equivalent internal resistance of two cells in parallel. Now I have to get the expression for equivalent EMF. This is the general expression. I have to particularly write what is epsilon EQ. So epsilon EQ, so I write equation 6. Equation 6, I can rewrite equation 6 as 6 becomes epsilon EQ equal to, okay, take REQ or RHS, REQ, then in the RHS take LCM. So that is R1 into R2 I write together, R1 into R2, and numerator will be epsilon 1 into R2 plus epsilon 2 into R1. Okay, so like that it becomes epsilon 1 into R2 plus epsilon 2 into R1. This is the RHS. Now further substituting REQ from the previous step, I can write epsilon EQ equal to REQ substitution. I have the single expression REQ here, that is R1 R2 by R1 plus R2 substitution. Okay, so in place of REQ I put this expression. So R1 into R2 divided by R1 plus R2, okay, into this bracket as usual, whatever it is there, epsilon 1 R2 plus epsilon 2 R1 divided by R1 into R2. Now you observe carefully, here R1 R2 numerator, here it is in denominator, so we can cancel R1 R1, R2 R2 cancel. So what happens is finally epsilon EQ is left out with the RHS. Epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2. R1 plus R2. This is the final expression for the equivalent EMF when two cells are joined in parallel. Equivalent EMF is epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2. Or else we can stop here itself. This also gives the equivalent EMF. Epsilon EQ divided by REQ equal to epsilon 1 by R1 plus epsilon 2 by R2. Equation number 6 also gives the same. Okay, then next, this is 7 I write REQ, and this is the 8th expression, last expression. Now in general, for n number of cells joined in series, we can extend the formula number 6 to n cells in parallel. Okay, so equivalent EMF can be written as epsilon EQ by REQ equal to epsilon 1 by R1 plus epsilon 2 by R2 plus third cell epsilon 3 by R3 etc. etc. continues up to n cell. epsilon n by Rn. This is the equivalent EMF epsilon EQ in case of parallel combination of n cells. Any number of cells, maybe 3, 4, 5 number of cells. And similarly, equivalent internal resistance can be written as reciprocal of internal resistance. Equivalent internal resistance is 1 by R1 plus 1 by R2 plus 1 by R3, so on, etc., etc., up to n cell 1 by Rn. All the reciprocals of internal resistance is added up to get the reciprocal of equivalent internal resistance. After adding the reciprocals, take again reciprocal to get the equivalent internal resistance of parallel combination of n cells. So this is the derivation here. The logic is very simple. Total current drawn from two cells is sum of the two currents. Then using the idea or relation between terminal PD, EMF, current and internal resistance, we can get the current I1 drawn from first cell, that is EMF minus terminal PD. The difference between EMF and terminal PD divided by internal resistance, that is the current drawn from any cell. Current drawn from any cell is the difference of EMF and terminal PD upon its internal resistance. So added two currents I1 and I2, then separating the terms, similar terms, epsilon 1 by R1 and epsilon 2 by R2 written in the first group of bracket within the bracket, and minus V by R1 minus V by R2 can be written as minus V common 1 by R1 plus 1 by R2. Then writing the similar relation for the equivalent cell. Okay, so the EMF minus IREQ is terminal PD. Terminal PD of the equivalent cell is EMF of the equivalent cell epsilon EQ minus current into equivalent internal resistance REQ. Then we can write current I equal to, from this rewriting mathematically like what I did in the first step, that is for cell 1. Same way we can write current I equal to epsilon EQ minus V, difference between EMF and terminal PD divided by the internal resistance is the current drawn from the equivalent cell. Then separating the terms, dividing separately, epsilon EQ by REQ minus V by REQ, equation 5 I get. Then for combination of two cells, equation 4, equivalent cell equation number 5, compare 4 and 5. We get epsilon EQ by REQ equal to epsilon 1 by R1 plus epsilon 2 by R2. We can write for n cells like this. Then equivalent internal resistance, compare here the second part with the V by REQ, same as V by 1 by R1 plus 1 by R2. V into 1 by R1 plus 1 by R2 is equivalent to V by REQ. Then I get 1 by REQ equal to 1 by R1 plus 1 by R2. Implies 1 by REQ, taking LCM of that. We get finally equivalent internal resistance as REQ is R1 R2 by R1 plus R2, and equivalent EMF is epsilon 1 R2 plus epsilon 2 R1 divided by R1 plus R2. This is all mathematics, nothing to do much with physics here. Actually, it is purely mathematical steps, okay, with the basic known ideas of physics. Then we will go to the next topic. Okay, so we have completed series and parallel combination of cells. Very important derivations, both the derivations in annual exam and in midterm exams for 3 marks. In case of series they ask for 3 marks, and in case of parallel they ask for 5 marks. Okay, so that's all about the two derivations. Next we have one more important idea, that is one more important concept given by Kirchhoff's. There are two rules or two laws given by Kirchhoff's. Kirchhoff's is the name of scientist. So Kirchhoff's rules or laws. Okay, Kirchhoff has given two rules. Kirchhoff's current law and Kirchhoff's voltage law. That is one for junction, it is called as junction rule or node rule. Another rule is for loop, then it is called as loop rule. Kirchhoff's loop rule or voltage law. Okay, now firstly in this where we apply this Kirchhoff's rules. First we apply Kirchhoff's junction rule, okay, or current law to a node or junction. Node or junction. So junction means in a circuit where more than 2 conductors meet. More than 2 conductors means there should be minimum 3. So if I have a junction like this, one conductor, say current I1 comes, another current goes I2 out from a junction, say A, and one current going out, say I3, current leaving this junction is I3, another current, say I4 getting in. So this point A, I can call it as a junction. Minimum 3 conductors or 3 branches meet at a point, then I can call that point in a circuit as a junction or a node. Junction or a node is a point in an electrical network where more than 2 conductors meet. More than 2 means minimum 3. 3 or more. We can also say 3 or more. Okay, 3, 4, 5 conductors or branches meet at a point or connected together, then that point is called as a junction. Now, junction A, say 4 currents are there actually. Some currents enter, some currents leave. So I1 is entering the junction A, I4 is entering the junction A, whereas I2 and I3 are leaving the junction A. Okay, so A is a junction here. Then we have another circuit definition term, that is called loop. Okay, loop. So what is a loop in electrical network? Loop is a closed path for the current flow. Closed path means once you start from one point traversing in the circuit, you should be able to reach the same point after traversing through some conductors or resistors or cells like that. You should be able to reach the same point. If the path is closed, okay, it is a closed path, then it is called as a loop. So we have node and loop in a circuit. These are the 2 basic terms. Okay, node or junction is a point, whereas loop is a closed path. Fine. Now firstly, I have Kirchhoff's junction rule or node rule. Kirchhoff's junction rule or node rule. Junction or node rule. It is also called as Kirchhoff's current law, or we can also call it as Kirchhoff's current law. So we can abbreviate like KCL. Okay, now in some books we can see this term, just applying KCL. Okay, KCL, applying KCL, applying Kirchhoff junction rule or node rule or Kirchhoff's first law also they may say. Okay, so to the junctioners, this rule is to junction or a node in the circuit. So diagram already I have drawn here. You can see a part of the circuit it is where 4 conductors, okay, 4 conductors meet at a point A of junction A. The Kirchhoff's junction rule or node rule says or states that the sum of the currents entering the junction is equal to sum of the currents leaving the junction. Sum means this SUM means addition of currents. Whatever currents are entering into the junction, total sum should be equal to the total current leaving the junction. So it is purely based on the term called conservation of charge. Charges cannot be created or cannot be destroyed. So this is based on the principle or significance of Kirchhoff junction rule. I can say conservation of charge. Significance or principle on which Kirchhoff junction rule work is conservation of charge. That means the accumulation of charges or production of charges at a junction is not possible. Okay, so that part we have to take care here. That is, charges cannot be created at a junction or cannot be destroyed at a junction. So whatever charges enter the junction, the same amount of charge leave the junction per unit time. So that is nothing but current. So the current entering the junction is equal to current leaving the junction. Sum I can say. Okay, sum of currents entering the junction equal to sum of current leaving the junction. Sum of currents leaving means going out, leaving the junction. So this is what the Kirchhoff's junction rule. It is based on the conservation of charge. We can also say that the algebraic sum of currents in a junction is 0. Algebraic sum of currents means whatever the current enters the junction, I have to take it as positive, and whatever current leaves the junction as negative. That way also I can express this Kirchhoff's junction rule. So according to this statement or wordings as given by the Kirchhoff's, I can write for this circuit part of the circuit. So currents entering the junction, adding, sum means adding, I said. I1 is entering, I4 is entering. So I1 plus I4 equal to sum of currents leaving the junction means going out. I3 is going out, I2 is going out. So I2 plus I3. Okay. So or we can also write I1 minus I2 minus I3 plus I4 equal to 0. This means which implies that algebraic summation of I equal to 0 at a junction. Algebraic summation of currents at a junction is 0. That is the currents taken with the proper sign plus or minus. Plus we take for current entering the junction, and minus sign we assign to the currents and leaving the junction or going out of the junction. So simple it is. Kirchhoff's current law or junction rule states that the sum of currents entering the junction is equal to sum of currents leaving the junction. This is based on conservation of charge. This is the Kirchhoff's junction rule. Next we have Kirchhoff's loop rule. Kirchhoff's loop rule. Okay, loop rule. So this rule is applied to a closed path or a loop. For example, I take one loop like this with some resistors. Okay, so one more cell I will take, another resistor. In this branch I will take only one resistor, and there may be some branches further here. So I will take in this loop, currents may not be same. Okay, so current I1 I will take here, current I2 I will take here for this. Okay, EMF epsilon 2 I will take epsilon 1, then R2, this resistance R1 and resistance R3. Current I will take in this I3. Okay, so like this I have a loop. This can be considered as a loop. So because it is starting from this point, if I take A, I go to the another point in the circuit, another junction B, another junction C, and I can come to the same point A. So this is a closed loop. Okay, closed path for the charge. Currents may not be same in the branches. Different branches have different currents. I1, I2, I3 I have taken. Now according to Kirchhoff's loop rule or Kirchhoff's voltage law, we also called it as KVL, Kirchhoff's voltage law, the algebraic sum of changes in potential around a closed loop involving resistors and cells in the loop is 0. Okay, let me write algebraic sum of changes in potential in a closed loop involving resistors and cells in the loop is 0. In the loop is 0. This is very important. 0. That means if you start from a point, change in PD, change in potential, one branch, another branch, like that, we keep on writing the change in PD. So net change in PD will be 0, because you may go from higher potential to lower potential, and again lower potential to higher potential. So that the net change in the potential for one branch, another branch added together algebraically will result in a 0 change in potential, because if you reach the same point means there is no change in the potential in a loop. Okay, now for this I will take clockwise traversing in this. Okay, so according to the clockwise traversing this circuit, this loop, for the part A, B, if I go from A to B, I can find a cell with EMF epsilon 2, current I2. Okay, so I am going from positive electrode to negative electrode, means potential here it is more, here it is less. Higher potential to lower. Normally current flows always higher potential to lower potential. So potential at this terminal should be less than this terminal. Okay. So potential here less, here more, means it will be less potential. And if I traverse in the direction of current, I have to take IR product as a negative, because the potential will be lesser here, more here. Okay, potential will be lesser here, more here. So now I am going along the direction of the current. So EMF and product of I and R here. So firstly EMF. If I come across firstly positive terminal of the cell in traversing, while traversing, then I have to take EMF as negative. So for the part VAB, okay, VAB plus VBC plus VAC equal to 0. VCA, okay, VCA equal to 0. That means VAB, potential difference between VAB, that is A and B, will be minus epsilon 2. EMF is epsilon 2 minus I take, because I approach first positive terminal, potential decreases in the EMF. Okay. Next minus I to R2, because I am traversing along the direction of current, then current into resistance should be taken negative. So minus I to R2. Okay, then okay, this is for VAB part. Then VBC, potential difference for VBC. Again I am going along the direction of current. So the change in PD between B and C, that means here potential is lesser. Current flows from greater potential to lesser potential. So less potential minus more potential should be a negative number. So minus I3R3. So minus I3R3. Okay, then C2A. Okay, C2A. Here I have current I1, resistance R1. Again in the direction of current. But the EMF, you see, I approach negative terminal first, positive terminal later. So EMF plus epsilon 1 I have to take. And product of current and resistance will be taken as minus I1 R1 equal to 0. So this is the expression we get by applying Kirchhoff's loop rule to the loop ABC. Okay, so we have to be a little bit careful here. In the direction of current, I into R, current into resistance for any part should be taken as negative. If you are traversing opposite to the direction of current, then I into R should be taken as positive. Then EMF of the cell we have to assign positive sign. For this case, because we approach first negative terminal, potential increases for the cell. Whereas if I go from here to here, I am going from higher potential to lower potential of the cell. Negative electrode means lower potential. So difference will be less minus more is a negative value. So that's why minus epsilon 2 I will take. Whereas for the cell 1, epsilon 1 EMF, I have taken plus, because here lower potential, here higher potential. So lower, here higher. Higher minus lower means it is positive value, epsilon 1. Okay, that's why the difference. I can say if you are going along the direction of current in case of a resistor, then current into resistance product, IR product, should be taken negative. If you are traversing opposite to the direction of current, then we have to take I into R product as positive. And here this Kirchhoff's loop rule based on the principle, that is conservation of energy. Conservation of energy we studied in first year also. Okay, conservation of energy says that energy can neither be created nor be destroyed. It can be transformed from one form to another form. Here energy dissipation in the circuit is zero. Okay, conservation of energy is the basic principle involved in the Kirchhoff's loop rule, and conservation of charge is the principle involved in Kirchhoff's junction rule. The two rules very important for next part also, that is Wheatstone's network. We are applying this Kirchhoff's loop rules. Okay, so that's the end of today's session.